3 is primarily we're going to talk about how to transform different functions, and we're going to focus eventually mostly on quadratic functions. That's kind of, we're moving into quadratics. This is a short unit. It's mostly about graphing stuff. Okay, and then we'll move into unit 4 relatively quickly, and that's going to be solving quadratic equations. Okay, but the first lesson, this 4.1 lesson, or 3.1 lesson, sorry, is a little bit strange. It deals with a completely different kind of function that we won't deal with really very much this unit after today. I mean, it'll be there on the test, but this one's a little different. It's called a piecewise function. Okay, and our goal for today is to be able to learn how to evaluate piecewise functions and graph piecewise functions, and that's it. And this other stuff we'll take care of later. Okay, so what is a piecewise function? Well, a piecewise function it's a function that's made up of two or more pieces, two or more individual functions, each with its own domain. So here's a couple of examples. Like example 1 here is a piecewise function that has 2 pieces. Example 2 down here is a piecewise function that has 3 pieces. Now, when you look at a piecewise function, let's make this a little simpler for a second. When you see something like this down here, everybody see where I'm pointing? The example 2 where it says g of x equals. When you see kind of an open-ended script bracket like that, that's there to indicate that you've got a piecewise function coming, okay? It means that we've got to have room for multiple rows in our function. There are multiple pieces. This top function only has 2 rows. There's the orange row and the purple row. So that's a 2-piece piecewise function. Example 2, notice, has 3 rows, and so it's a 3-piece piecewise function. It's got 3 individual pieces. I'm going to cover this one up for now, though, so it doesn't look so confusing. Let's just focus on this simpler one for a second. So this piecewise function has 2 pieces, the orange piece and the purple piece. Now let's focus on just the orange piece for a second. So we're only looking inside the orange box. The top row of this piecewise function, which we'll call the orange piece, has 2 parts, like all piecewise functions. It's got the function part that tells me what the graph looks like. So this top function has a graph x squared minus 1. I know that's quadratic. Don't worry, we're not going to be dealing with quadratics until I'll show you how to do this stuff with technology on Friday. And then you could do a piecewise function with quadratics because Desmos will make the graph for you. But otherwise, when we're graphing these things manually, we'll only have linear equations, so they're easy to graph, okay? But in this first example, we're not graphing it anyway. So we'll use a quadratic up here. So the orange piece is the function x squared minus 1, but notice the second part of the orange box. It gives you the domain. In this piecewise function f of x, we're only going to graph eventually this quadratic function, so it's going to be a parabola, right? We're only going to graph that for certain input values. So we're only going to graph it on the orange domain, which is the values of x that are less than -2, okay? Let's look at the purple piece. The purple piece is a simpler line that we're going to graph, but once again, we're only going to graph that on its own domain, which is when x is greater than or equal to -2. Okay, well, let's not focus on graphing yet. Let's stick to just evaluating the function, right? Evaluating a function is no big deal. You've done that a lot. That's one of the easier things that we do in math. When you evaluate a function, essentially, it's just plug and chug. Right? You're just going to take an x value and plug it in for x and see what you get. So when we ask something like part A here, what is f of -5? That's saying it wants us to tell what the output of that function is going to be when I input a -5. Okay, but this is a little bit more, very slightly more complicated than what we've done in the past. Because now we've got 2 different pieces of our function. And so how are we going to do this? Are we going to plug the x value into both? Or are we just going to plug into one or the other? How are we going to know? Anybody have a suggestion? Where should I plug that -5 in my piecewise function? And just maybe type it in chat. Why doesn't everybody give me an answer? If you possibly can, give me an answer in chat. Where am I going to plug that -5? top or bottom or both? And I haven't told you yet, so you may be wrong, but that's all right. I'm going to tell you. Okay, I'm seeing a both. I'm seeing some boths, question marks. Yeah, you've never done this before. How would you know? Okay, I'm going to give you a hint, though. I'm going to remind you about something I've already mentioned, and that's the domains. The orange piece only exists for x values that are less than -2. So it only includes input values of x less than -2. The purple piece only includes input values of x that are greater than or equal to -2. So do you want to change your answers here? What do you think? Where am I going to plug that -5, that input value of x, that -5? Where am I going to plug that now, top or bottom? What do you think? Is -5 an x value that's less than -2? Give me thumbs up, thumbs down, or just type a yes or no in chat. Is -5 less than -2? Yes or no? It is, isn't it? Right? It is. Is -5 greater than or equal to -2? No, it's not, right? So the -5 must get plugged into the top piece because it fits with that domain. It's an x value that's less than -2, right? So because -5 is less than -2, we're plugging it into the top piece of the piecewise function, right? And so what are we going to get then? Well, I'm going to end up with every place I had an x, I'm going to plug in a -5. So I'm going to get -5 squared, which is 25, minus 1 is 24. Everybody see that? Okay. Let's skip over to part C. What about f of 7? So it's asking us to plug 7 into my function and determine what the output is going to be. That's what f of 7 means. So where am I going to plug the 7 in, top or bottom? Type it in chat. Quick. Everybody's got to answer. If you're not sure, just give me a question mark. That's okay, but give me top or bottom for part C. Top or bottom? Where am I plugging that 7? Top or bottom? Ooh, we're kind of converging on, it looks like on bottom as an answer. That's correct, right? Because 7 is greater than or equal to -2, isn't it? Because 7 is greater than or equal to -2, we're going to plug it into the bottom. So we're just going to get 5 times 7 is 35 plus 3 is 38. Okay? But give me a 1 to 5 on that. Either flash me fingers or give me a 1 to 5 in chat. Okay, all right. We're getting there. This is normally a tricky section because it's so different, but you guys are doing great. So let's look at part B then. What about -2? F of -2, where does that one get plugged in? Top or bottom? Is -2 less than -2, or is it greater than or equal to -2? That determines your answer. So in part B, where do I plug the -2, top or bottom? Everybody quickly give me an answer on that. I've gotten 6 answers, but I should get like 24 answers. Okay, I'm waiting. I haven't gotten an answer from everybody yet. I want an answer. Where do I plug that -2? Okay, that's still not everybody, but I'll leave it there. So yeah, it goes in the bottom, doesn't it? Because -2 is greater than or equal to -2. It's equal to -2, right? So therefore it's greater than or equal to -2. Plug it in the bottom, I get 5 times -2 is -10 plus 3 is -7. Okay, and we got it. All right, so that's how we evaluate piecewise functions. Now let's work on graphing piecewise functions. And I'm going to take you through this slowly. But at the end, you're going to get this. If you just pay attention here, you're going to get this at the end. So we need to graph, ultimately we want to graph the top piece on its domain and the bottom piece on its domain. But maybe let's start off this just by first of all, let's not even worry about anything in the purple box. let's just graph the bottom piece. So on the top, we've got the line y equals negative 3x minus 3, right? You can call it y instead of g of x if you want to. So that's a line. Help me graph that line, somebody. Let's see. How about Akira? I want to graph the red line. Where am I going to put my first point to graph that red line?
On the -7.
Okay, on the y-axis at -7. Good. So we'll go down. There's my y-intercept. Very good. Okay. How am I going to get another point?
And then you'll go down 3/1.
Okay, down 3/1. That's not very convenient, though, to go down 3 and over 1. So what could I do instead?
Go up 3 and then to the left 1.
There you go. Go up 3 and back 1. Good. Okay. Perfect. So there's my 2 points. That's all it takes, right? To define a line, I just need 2 points. And so now I'll connect and extend those 2 points. And there's my line, right? There's the red piece. That's what the red piece looks like. It's graph, correct? Okay, what about the bottom one? Well, the bottom one is really simple. It's just y equals -5. So where's my y-intercept for that bottom one, Brogan? If the whole equation is y equals -5. That's also in slope-intercept form, if I want to think of it that way, isn't it? In the form mx plus b. But what's m? What must I be multiplying by x if it doesn't show up? You guys can just type it in chat if you want to. What's the value of the slope in the blue piece, that blue line? Yeah, there it's showing up. It's got to be 0, doesn't it? Because when I multiply by 0, the x term just goes away. So the slope is 0. The y-intercept, Brogan, is what then? For the blue piece.
0?
No, that's the slope. It's mx plus b. It's 0x minus 5. So what's...
I'm not sure. Would be 1, I guess?
It'd be... So it'd have to be -5 then, right? Because that's the constant. Okay? So my y-intercept is -5, and my slope is 0. So I'm just going to graph a horizontal line then, aren't I? But remember, this is consistent with what we did previously too, though, right? Because when we have the line y equals a constant, remember what that means. That means all of the y coordinates of every point on that line has to be -5. So it has to be a horizontal line, doesn't it? That passes through the y-axis at -5. Okay, so there's my there's the 2 graphs, right? The graph of the red function and the blue function. But now let's focus on this purple part. So look what's going on here. The top piece is defined for x values that are less than -1, and the bottom piece is defined for x values that are greater than or equal to -1. So what is the x value that acts as a boundary between the 2 pieces? McKenna?
Would it be where they go together?
Yeah, what is that x value?
A half.
Well, now look, let me say this again. So the red piece is what we graph for all x values that are less than -1. The blue piece is what we graph for all x values that are greater than or equal to -1. So if an ant were walking along this piecewise function, he would be walking on the red piece for every x value less than -1. He'd be walking on the blue piece for every x value greater than or equal to -1. So where is he transitioning from the red piece to the blue piece? At what x value?
I'm not sure.
It's what's the common number there, right? It's when x is less than -1, he's on the red piece. When x is greater than -1, he's on the blue piece. So isn't that -1? Isn't that the place where he's making his shift from one to the other? Does everybody agree with that? Okay. So that's going to be my boundary. -1 is the point, is the x value where I'm transitioning between pieces on my function. Everybody see that? So I'm going to put a boundary there, right? I'm going to put a boundary line at -1. And the vertical, that is a vertical line, isn't it? X equals -1 is a vertical boundary line. And so that's going to be the partition between the red piece and the blue piece. Everybody see that? Give me a 1 to 5 on that, please, quickly. Okay, we're good. That's good. So there's my boundary piece. Now my goal is, even though I graphed the entire line, y equals negative 3x minus 7, and I graphed the entire line, y equals negative 5, I really only am supposed to graph the red piece in its domain. We'll call that the red region. That's going to be every place to the left of that, my boundary line, isn't it? Because where is x less than negative 1? It's less than negative 1 to the left of my vertical line. Everybody agree? Right? Now, if I had given you this problem a week ago, if I'd said, I want you to graph the inequality, right? If I want you to graph the inequality, x is less than negative 1, what would you have done? When we graph an inequality, we need a boundary line and a shaded half plane, right? Well, my boundary line would just end up being the line x equals negative 1, right? And so if this is negative 1 on the x-axis, you would have told me to make a vertical boundary line that's dashed, right? Doesn't that make sense, right? We did all this stuff last unit. So I would have had something like this. And then you would have told me, based on the direction of this inequality, I'm graphing the x values that are less than my boundary line. You would have told me to graph everything. Oops, that's what I want. You would have told me to graph everything over there, wouldn't you? Right? Doesn't that make sense? Okay, well, that's really all we're doing here, right? We want the red region is the region where x is less than negative 1. So I'm just going to shade that entire region in the xy plane to the left of my boundary. I'm just going to shade it red for now, right? Because that's the region where I'm going to graph the red piece. Well, doesn't that mean I really only get to keep my graph right there, don't I? Even though that line goes forever, because I'm only keeping the piece of the line to the left of my boundary, the piece that's defined where x is less than negative 1, I only get to keep that dark red ray. I don't get to keep the whole line. Everybody see that? Give me a 1 to 5 on that. That's a really important concept. Okay, good. Now, what about the blue piece? Well, I'm going to graph the blue piece where x is greater than or equal to negative 1. So isn't that going to be the region to the right of my vertical boundary, right? So I only get to keep the graph of that blue line right there, right, to the right of my boundary. So I only get to keep that. I only get to keep that blue ray. I don't get to keep the whole blue line, right? So that's what my piecewise function graph is going to look like. But there's one more thing we got to deal with. What about the endpoints? Now, for the red piece, it's defined where x is less than negative 1. The blue piece is defined where x is greater than or equal to negative 1. So what kind of, and type this in chat, everybody, what kind of endpoint do I need for my red ray here? Open or closed? If I'm not including x in the red piece. I should get an answer from everybody on this. Yeah, it's open, isn't it? Okay, so there's the endpoint I get for my red piece. How about for the blue piece? The blue piece is defined when x is greater than or equal to negative 1. So what about the blue piece? What kind of endpoint am I going to have there? Yeah, it's closed, isn't it? It's closed because x equals -1 is actually a part of the blue region, isn't it? Right? So there's my graph. I got it. Ta-da. Okay, but there's a couple more things I'm asked to do here. I want to identify the domain and the range also. Okay, so the domain is the set of all the x values in my graph, and the range is the set of all the y values in my graph. Okay, so we've talked about this a couple different ways to help people conceptualize it. One thing we've said in the past is think of all the different x values that an ant could stand on when he walks on this piecewise function. Well, the ant can walk on both of the two pieces, correct? He can walk on the red piece and the blue piece. So that's one way to think about it. Another way to think about it is to project the function onto the x-axis. Okay, and I figured out a way to do this. This is kind of a cool way to do it with these flip charts. It allows me to do this visually, and I think this is a good way for you to see this, right? If I take this red piece of my piecewise function and I project that onto the x-axis, what's that going to look like? It means that every single point on this red piece of my piecewise function is going to get smashed vertically up or down onto the x-axis. So it's going to look like this. So like this piece right there is going to go straight up to there. This piece over here is going to go straight down. But wouldn't you agree that because that red piece goes forever, the projection is going to go forever to the left? Okay, but it does have an endpoint at the right, right? The projection stops at and doesn't include x equals -1. Right, so there's the red projection. Everybody give me a 1 to 5 on that. That's the red projection onto the x-axis. So that dark red line, and let me make an arrow at the end of that, how about? To remind us that this one goes forever to the right, to the left, sorry. You got my directions mixed up here. Oops. That's what I want. There's my red arrow, okay? Okay, give me a 1 to 5 on that. Does that make sense? Everybody. So that's my red domain. That's the red projection of the red piece onto the x-axis. Okay, and you could just do that in your head. You don't have to do it on paper, right? You can. Okay, what about the blue projection? If I projected the entire blue piece onto the x-axis, that means I'm just smushing it, the whole thing straight up onto the x-axis. And that's what I get, right? That blue endpoint fills in, the solid blue endpoint happens to fill in the red open endpoint of my domain. And then wouldn't you agree that if I graph the entire domain, both the red and the blue pieces in green, it just looks like the entire x-axis, right? The piecewise function covers the entire x-axis when I project it onto the x-axis. And so my domain is all real numbers. Okay, everybody see that? 1 to 5. Everybody. Show me your here, please. Okay, good. And see if we could now, let's go back a couple steps to there. We could do that in our head, couldn't we? If we want to project the red and the blue pieces onto the x-axis, we can see that everything's going to overlap, and I'm going to cover the entire x-axis. So we end up there. Okay, now let's do the same thing for the range. We're just going to do the same thing onto the y-axis, right? We'll project the red piece and the blue piece onto the y-axis. So if I move this guy horizontally onto the y-axis, it's going to start at -4 and just go up forever, right? It goes up infinitely far. So we end up with something like, it's doing that, right? It's going up forever. And it's got a lower endpoint down here at -4. Okay, so there's the projection of the red piece onto the y-axis. So that's the red domain. What's the projection of the blue piece going to look like when I squish the whole blue piece onto the y-axis? That's going to be kind of strange looking. Anahi, what's that going to look like? If I take that entire blue horizontal ray and squish it onto the y-axis, what do I get?
A straight line.
Yeah, well, in fact, I'm just going to get just a point, aren't I? Right? Because this whole thing is just getting smushed. Every point on that blue line, when I squeeze them into the y-axis, they're all going to end up at the same place, which is just right there. I only actually end up getting 1 point, right? The entire blue range is just the y value -5. Everybody see that? Okay. So then if I want to, let's take the red range and the blue range, and let's combine them into one purple graph. I just get something like that, don't I? Okay. And so if I wanted to write the range, then the range is just, I'm gonna have to have a comma. There's two pieces. It's going to be -5 is one part of the range, comma, there's another piece, which is an interval. It's the interval where y is greater than -4. So it'd be the interval where I'd have to have parentheses because I'm not including the endpoint, then a -4, comma, infinity, because it goes up forever. Okay, if I wanted to say that using inequalities instead of interval notation, I would say it like y equals -5 or y is greater than -4, right? Everybody give me a 1 to 5 on that. That's a little trickier one. Okay, and we'll look at more examples. So we'll get some more practice with this. I want to really focus on this one example, though, for now. Okay, good. So there we go, right? We got our answers. There's all our answers. We're done with problem 4. But I think we can do it a little better. I think we can be a little more efficient with this. I wanted to go through all those steps, but now let's go back and see if we can engineer this process a little bit better. And here's where I think we can cut a little time and make this a little bit easier. Did we really need to have this first step where we graphed the entire red line and the entire blue line, right? We probably didn't need that because we ended up only keeping a part of the red line and a part of the blue line, right? Wouldn't it have been better if when we were getting our 2 points to define each of these lines, what if I had just picked points for the red piece that were in the red region, right? And I picked points for the blue piece that were in the blue region. That would have cut a step there, wouldn't it, right? So let's try that. Okay, we could do that with t-tables. Okay, we know that the red region is where we're graphing the red piece, which is y equals -3x minus 7, right? So let's just pick 2 x values to plug into my function that are in the red region. And the easiest way to do that is with a t-table. What is one x value that for sure we want to have? Because think where we're going with this. I want to have 2 points in the red region that I can connect and extend to the left to create the red ray, right? To create this red ray that we ended up getting, okay? Well, where should one of those points be for sure if I want to make an accurate picture? Well, just think logically. This isn't a math question. This is just kind of a logic question. Where should you put one of those points? What do you think? Gabe, Brown, you got an idea? Oh, okay, I'm seeing some answers. Good answers. What do you think, Gabe? You have an idea?
What was the question?
What x value, what's an x value I definitely want to use to create one of my red points? To create my, I'm trying to build, this is the answer, but we want to get there, right? I want to build the red ray. I want to graph the red piece in the red region. -1, I definitely want to include because that's at my boundary, don't I? Right, so if I plug -1 in to the red piece, I'm going to get -3 times -1 is +3, minus 7 is -4, right? Now look at that. That's an ordered pair, right? When we use t-tables, one of the advantages of a t-table is that the x and y values just look like ordered pairs, don't they? Right? So I've got the ordered pair, -1, -4. Okay, so that's the point that goes on the boundary. Because we're not including -1 in the red region, I'm going to have to use an open endpoint, but I'm going to put it at the coordinates from the origin. I'm going to go back 1 and down 4, and there's 1 point. Everybody see that? Right? And then for my other one, I could pick anywhere. I'm going to pick one that's a little bit further away just so it's easier to graph the line, right? It's a little more accurate if I've got points that are spread apart a little bit. So how about if I pick the x value -4 and plug that in? So -3 times -4 is +12, -7 should be +5, right? So I get the ordered pair -4. So from the origin, I'm going to go back 4, and I'm going to go up 5. 1, 2, 3, 4, 5. So there's my other point. And now all I would have to do is create a ray from my boundary point. What did I do wrong here? 1, 2, 3, 4, up 5. I think my ray's just not shaped right. I'll just do that. I'll change it. How's that? There. Okay, everybody agree? That makes sense? Did I have to pick the point -4? No, I could have picked any point, right? I could have picked the point if I wanted to. I could have picked the point -2. If I plug -2 into my function, I'd get -3 times -2 is +6 minus 7 is -1, right? I would have gotten the point -2, -1. So -2, that would have just made a point right there. Well, that's still on my line, isn't it? That would have worked. There's no magic. That second x value, there's nothing magic about that. I just kind of picked one out of the dark, right? Okay, 1 to 5 on that. Okay, good. That's a little quicker and better though, isn't it? If we pick the points in the red region, I didn't even have to graph the whole red line and then erase it, right? Okay, what about the blue region? Now, this is an easy one. We just get y equals -5, right? Well, we know what that looks like. I want to pick an endpoint. I definitely want to pick x equals -1. It's a little weird, though. Where am I plugging the x value into my function? Well, there is no x value in my function. So whatever x value I pick, the output is always -5. So there's one ordered pair. At -1, -5, I'm going to use a solid endpoint because the blue piece, the blue region includes -1. So I've got the starting from 0, 0, I go back 1 and down 5. And then I could pick any x value I want. It doesn't matter. The y value is always going to be -5. So maybe I pick one where I go over 4 and down 5. It doesn't matter, right? Now I'm going to connect and extend to the right to create my blue ray, and I'm done. Okay, 1 to 5. Okay, good. All right, let's try another example. Let's maybe try one that's got 3 pieces here instead. Okay, so first of all, let's see if we can figure out where are my boundaries going to have to be between the 3 pieces. I'm going to need 2 boundaries, aren't I, between those 3 pieces. So where am I transitioning here? The ant is walking on the top piece whenever x is less than or equal to -2, but when x passes through -2, he moves to the middle piece, right? And that's where the ant is walking for values of x greater than -2 and less than 4. So when x is between -2 and 4, he's walking on the middle piece. And then when he gets to x values that are bigger than 4, he's jumping down to the bottom piece. So type in chat, what are the x values where I'm making transitions between the pieces? What are my boundary lines going to be? What x values? Type it in chat. What are my boundary lines going to look like here? Aurelia, what are my boundary lines going to be? Help me out.
Are they going to be negative 2 and 4.
There you go, negative 2 and 4, right? Everybody see that? Look, I'm making one transition here at negative 2, right? That's where I'm making one transition. So I'm going to put one boundary line at negative 2, and then I'm making another transition here. Oops. At 4, right? When x passes the value 4, I'm making another transition, and so I need another boundary line there. So the top function is going to exist in this region for x values less than, meaning to the left of negative 2 or equal to. The middle piece is going to exist between x equals negative 2 and x equals 4, so it's in this middle region. And the bottom piece is for x values greater than, so to the right of 4. Okay? All right, so let's color code these. Let's deal with we'll call the top piece the red piece, right? So we want to graph that in its region, okay? So in its region, oops, don't want to have that shown. Right, so there, everybody agree that's the red region. The x values less than or equal to negative 2, so I'm in this region. So let's pick 2 points in the red region so we can graph the red piece in its region, okay? Emily, give me one x value I need to include. Questions for Emily?
Not sure.
Not sure? Okay, so if I want to pick 2 points to graph the red ray, I probably want to know where it is when I'm at the boundary, don't I? Right? Does that make sense? I mean, so do I really need to include it? I mean, I guess I don't need to, but it's smart to include it. I should include the value negative 2, so I know where the red piece bumps into the boundary, right?
Yeah.
Okay, so if I plug negative 2 in, 4 times negative 2 is negative 4. So there's 1 point, right? Now, in the red region, I'm including negative 2. So am I going to use an open or a closed endpoint?
It's going to be closed.
Closed. Okay, good. So I'm going to put a point at negative 2, negative 4. So there's 1 point right there. And now I can pick any one I want to. Well, let's just pick negative 4. How about? So if I plug negative 4 in, 2 times negative 4 is negative 8. And so I've got another point, and that's going to be closed also. Obviously, that's closed, right? Because it's inside the red region. And so we go from the origin, we're going to go back 4 and down 8. And then all I've got to do now is just connect those. Oh, hang on one quick second here. Okay, so then all I've got to do now is just connect those with array, right? So we've got something like that, right? So there's my red piece, okay? So let's move on. Now we want to do the blue piece, right? So the blue piece, the blue region is going to be between my boundary lines. So that's my blue region, right? I got to graph that blue one. So this time, probably, what should maybe Mr. Thatcher, what should my X values be here probably? What would be the smartest ones to pick?
Did you say mine?
Yep.
It's really laggy for me.
Yeah,
Right.
yeah, you.
So for the blue,
Mm-hmm. I just need values in the blue region, but which ones would probably make the most sense?
-2.
Okay, good. -2 would be a good one. If I plug -2 in, I'm going to get -1 minus -2 is +2. So I'd get the point -2, 1. I'm not including -2 in my blue region, so that's going to have to, that's going to have to be an open endpoint, right? Uh-oh, what'd I do there? Come on, there we go. So -2, +1 is right there. And then what other one would make sense, James?
+4.
+4, yeah, it'd be a great one, right? If I pick 4, I'm going to get -1 minus 4 is -5. And those two make the most sense, don't they? Because then I'm actually picking the ones that are going to be, come on. Why won't this let me? I don't know what this is doing. Let's pick that guy. Oh, that's not what I want to do for sure. Well, anyway, you guys have got to go. Oh, there we go. Okay. Well, anyway, I'm wasting your time. Oh, got it. Okay, so negative or +4, -5. So there it goes. And then all I'd have to do is just connect those points, and it'd look like that, wouldn't it? Okay, that's where we leave off for today. The bell rang. I'm here after school if you have any questions at all. Otherwise, I'll see you on Friday. Have a great day.